I'm going to start with some very basic info on induced polarization, which is essentially effects of charge storage. So if we think of simple electrical circuits, if you have two conductive plates separated by an insulating material, you can get, and you apply voltage to it, you get charges set up on the sides. And that sort of charge separation has got stored energy. And if you remove the voltage source, if you sort of open it up, that charge will just stay in the capacitor. If you replace the voltage source by a short circuit, it'll discharge. So induced polarization is essentially just how charge separation can occur in materials. Now, the next step up from that simple electrical capacitor is if we have some sort of pore or tube containing ions, say sodium chloride, so it's slightly saline, and that tube is blocked by an electrolytic conductor, and we apply a voltage, well, conductors will let electrons cross. And so what happens is it's slightly different from the capacitor we showed before. Current will flow through, and so electrons will flow through the conductor, and you'll get a buildup of charge either side. The side of the conductor that's negative will attract positive ions from the fluid. And so you get an excess of positive and negative ions on each side. So the ion diffusion is slower than a capacitive buildup. And this process can happen two ways. One is electrode polarization, illustrated on the left, where ions are blocked by a conductive mineral grain. And the second case, which I won't be talking about much, is membrane polarization, where ions accumulate near charged mineral surfaces without the need for complete blockage. So there's many geological sources of induced polarization. Top right, there's graphite, that's an electronic conductor. Magnetite on the left, which is an electronic conductor if the grains are connected, which typically happens in mobile belts and not many other cases. Massive sulfides, like the bornite shown on the right, in the middle, are conductors as well. Manganese dioxide, bottom left, is also a fairly common electronic conductor. Things like native copper and not uncommon. It was the source of the target of the Ernest Henry discovery. Other potential geological pipes as well, which are conductive and or have an IP response. For membrane dielectric polarization, there's two common sources. There's clays, which have sort of planar grains with charge surfaces. The second common case of dielectric polarization is permafrost and ice. And that was the cause for many of the IP anomalies seen at the kimberlites in northern Canada and northern Siberia. Just sort of ice IP effects. Okay, so if we have mixed ionic and electronic conductors, the amount of diffusion you get is controlled by several factors. First of all, the size and shape of the electronic conductor grains. The smaller they are, the quicker things can happen. Second, the constitution of the ions. For example, chlorine minus is twice the size of sodium plus. So it's much easier for the chlorine to move than it is for the sodium. Sorry, vice versa. So that affects exactly what happens. The third factor that comes in is chemical reactivity at the surface. If ions are dissolving and coming off the electronic conductor or not, that makes a difference. And fourthly, geometrical complexity of the porosity and pores containing things. So, but whatever the complications are, it's an energy storage mechanism. And the IP effect has got, if you switch off the applied voltage and things return to equilibrium, you get reversed current flow. So if we have a voltage or a current we apply to a sample and turn it off, so it's a step change, there's two fundamental types of decays. If there's no electrochemical reactions or charge diffusion present, you get exponential decays. The charge disperses with an exponential time constant. And sort of pure physics like resistors and capacitors, the time constant of decay is sort of consistent with delay time. It's always the same exponential decay. The second type of response is called Warburg decays or diffusion decays. They are typical for sulfides and clays. And initially, a Warburg decay is faster than an exponential, and then afterwards it's slower. And the expression for that is given for those that like complementary error functions and square roots. You don't need to worry too much about it. But the physics behind that is electrical double layer physics with chemical diffusion inference. Okay, this is all the hard stuff is at the front. We'll get onto more descriptive stuff afterwards. But IP effects traditionally fit with Coe models. They fit the frequency dependence initially of dielectrics, which were introduced by Coe and Cole in 1941. Epsilon is the dielectric constant. Epsilon infinity is the high frequency response of that. Epsilon zero is the low frequency response. Omega is the angular frequency. That's a time constant. And the C is an exponent, which is just something that they initially fit to models. That same expression can be used with resistivity instead of dielectric constant, which is the one that Pelton used, except he rearranged it. Most traditional IP equipment measures rho zero. It doesn't have high frequencies. And using the expressions for chargeability, which is the difference between low and high frequency limits, normalized, Pelton derived this expression, which is what you see most commonly, but it is numerically identical to this expression on the left. You can also make a Coe equation for conductivity, which is the inverse of resistivity. And for all of these, the differences between high and low frequency response are either given by a polarizability given by the symbol eta or a chargeability given by M. C is sort of invariant. I won't get into that sort of too much. But what's interesting is all of these any of these expressions can be used to fit data. But when you do that, it turns out the time constants are different. And the conductivity time constant is equal to the resistivity time constant times this expression, 1 minus the chargeability m, which is a number between 0 and 1, to the power 1 upon c. So if you read papers on it, people seem to think that all these time constants are roughly the same, but I'll show you that they're not. So coal bottles fit most lab IP data collected over 6 to 9 decades in frequency. This is 3, 6, that's 12 decades in frequency I'm showing here. So I'm going to look at one Tasmanian massive sulfide example at the top right-hand side. That had a chargeability of 0.96, a time constant of 10 days, and a frequency dependence of 0.25. So you might think, gee whiz, if we're only measuring for a couple of seconds with our standard IPEGA, would we see it? And, whoops, what's happened? If we come back to this equation and use the conductive time constant rather than the resistive one, and we substitute in the numbers charge minus 0.96 is 0.04, C was 0.2, so that's the fifth. We get a time constant of 88 milliseconds. Which is something that an EM system might see. So this is a property depending on whether you excite things with a current or a voltage source, as I'll explain in a moment. You can either get a 10-day time constant or an 88 millisecond time constant. So just looking at some coal responses, I've taken a frequency dependence of 0.25, a time constant of 20 milliseconds, and I'm varying chargeability. If we take, look at the imaginary conductivity, all of those peak at the same frequency of 20 milliseconds with a time constant of 20 milliseconds or frequency of 1 upon 2 pi times 20 milliseconds. So frequency is roughly 10 hertz. Roughly 10 hertz. If we looked at the imaginary resistivity, the time constants we would get by increasing chargeability, which is just increasing the volume of polarizable material, will go from 28 milliseconds up to 16 days if you get a lot of polarizable material. I won't talk about the frequency time constants as to save sort of time in this this presentation. Okay, so why have we got such huge differences in time constants and how might we measure them? I'm going to look at some equivalent circuits. I would hope that most of the audience has some basic electronic knowledge from first year physics or something similar. So I'll try to help you to understand why the time constants are different and which of them is best. So Pelton introduced a blocked pore bottle. If you have some mineralized rock with a pore in it, on the right is a photomicrograph of a thin section of rock. So the greenish stuff is resistive olivine. The black is slightly conductive pores. There's sulfides in that of pyrrhotite, pentlandite, and chalcopyrite. And there's something like a 21 variation in grain sizes, which is in single dimensions has about a 400-to-1 variation in area and 4 decades of variation in grain volumes that you can see. So grain sizes vary a lot. We'll see how that changes time constant shortly. So Pelton approximated response of the black in this thing with pores, as shown here, blocked by mineralized grains, and said there's an equivalent circuit with a resistor on the top, another resistor through here, and this blocking element for which he put a sort of a reactive thing, which could either be a capacitor or a Warburg type of impedance. So, and the response of this reactive component is given by this expression for conductivity. So I'm going to make a further simplification. I'm going to say these pores are about the same size, so we can approximate both by the same resistivity. So here's the basic circuit. We remember voltage is current times resistance. If between terminals A and B, the resistances are in parallel, so the total resistance is just half the individual ones. And if you apply a voltage, you get a current 2V upon R. So capacitors conduct while charging or discharging, resistive otherwise. So if we now introduce a capacitor on the circuit and apply a voltage, that circuit has two different time constants, which is where the differences between tau conductive and tau resistive come in. And by time -1, our voltage is off. Then we're going to turn it on at time 0. So the voltage jumps to V. So this was a discharge capacitor, so it's got 0 resistance. So the initial current, 2V upon R, flows equally through top and bottom. So after time 0, V stays constant, and the capacitor charges with a time constant RC. And eventually, when that's fully charged, all the current flows to the top thing, so it reduces current to V upon R. So the time constant for this is just RC. Okay, now if instead we turn on a current, so we've got something that's driving a current through this. At time 0, the current jumps to I. So the initial voltage is I upon 2 because the current flows equally through the top and bottom. After time 0, the current stays constant. So the current charges until all current is flowing in the top path. So the measured V is now IR because all the current's just at the top. So voltage slowly increases through the circuit, and it actually takes twice the time to fully charge the capacitor. If resistances have different values, you can vary this with relating resistance to chargeability, which I won't get into. If we increase the number of blocked paths, that changes the resistances, it changes the timing, and increases the chargeability. So I won't wade through this because there's other things I want to get into. You can work through this. There's a recent paper published in Geophysical Journal International which covers this, which I'll send to Stephanie for reference if you're interested in the math. That's the one to look at. Okay, but anyway, the time constant T sigma for a voltage source is independent of chargeability. It doesn't matter how many of the grains are blocked. you get the same T sigma. The Pelton resistivity formulation, the bulk scale depends on the chargeability. So simple circuits also work for things like 3D conductive spheres. In that case, chargeability is given by the volume fraction, approximately 9 times the volume fraction upon 2. And if you have different size polarizable grains, you get a mixture of local time constants. Okay, for people who've studied IP, they look at Pelton's paper, where he looked at log measured time constants and chargeability. This is just lab samples of sulfides. And he measured time constants from 10 microseconds up to well over a few thousand seconds. So 20, 30 minutes, he measured sort of half-hour time constants. Other people, as I say, have measured time constants of days using T-row. If instead of the current source he'd used a voltage source, then this is what T sigma looks like. All the time constants are less than 10 seconds. The longest ones are just a few seconds rather than tens of minutes. And you get increasing volume percent of sulfides increases chargeability. Increasing grain sizes is increasing time constant. Things are much simpler. So I'll come to a field example of this. These are measured time constants of permafrost in the Arctic. So blue was predicting is the measured sort of T row that was calculated originally. If we transfer that from modeling to T sigma, then instead of time constants up to 200 microseconds, we get a much tighter time of constants around sort of 30 microseconds. This is also true from, well, don't worry about the bottom one, but field data shows this is the case. We should be using T sigma, which is the voltage source rather than the current source. Okay, so this picture on the right was from Wong's electrochemical model plus lab data, where they looked at T sigma as a function of grain radius, and all the samples fit in very nicely, independent of chargeability. So life is simpler with T sigma. Chargeability increases with a fraction of Black's pores in a resistive host, or the volume of polarizable material if you've got a conductive host. T is proportional to the area of the double unpolarizable lens, so it's essentially grain radius squared. And T sigma is much shorter than the phase time constant, and also much shorter than T row, the usual IP time constant. So days or weeks in the literature become seconds or less if we calculate or measure T sigma. Okay, so I'm skipping this. So the question is, can we make field measurements with a voltage source rather than a current source? All conventional IP injects current into the ground. And the answer is, if we have an inductive source, it creates, with a changing magnetic field dBdt, then circulates a circulating current in the ground, and that creates magnetic fields. The caveat is the ground has to be conductive enough to get current flow. So you get circulating electric fields from the changing magnetic field. Okay, so 1970s, the first IP effects were seen with coil sensors, DPDT, so not magnetic fields, but changing magnetic fields. Those were proven to be IP effects, and all of the early stuff, they only arose from shallow sources. So if you do some modeling to compare the electric fields in, say, a 50 ohm meter half space from a 1 million amp meter squared magnetic dipole source, so either a ground loop of a kilometer square carrying 1 amp, or an airborne, a very powerful airborne transmitter, some of which exist at a million amp meter squared, the fields in the ground are about half the amplitude at 50 meters depth of the fields we get from injecting the current between two electrodes. So a magnetic source can produce similar currents in the ground to current injection at 50 ohm meter host. It's the more resistive it is, the less so don't worry about that. Okay, in 2003, GATEM flew a survey in Tasmania, and the IP effect there showed up as negatives, and it showed up much more strongly in the X component, dBx dt, because it's measuring with a coil, than the vertical component. So GATEM had a separated geometry with a toad bird. So as well as the coincident loop negatives, there was evidence in the early 2000s that toad bird systems could also see clear IP in the X component was bigger than the Z. Why is that the case? If we have a transmitter 30 meters above the ground that induces current in the ground, which at early delay times is close to the source, and that moves downwards and outwards. So you have to be about 300 meters out before the current sort of center is down about 100 meters in a half space. So a vertical component receiver is most sensitive to the shallow currents near the source. Out at this distance, if you have current flow into the screen at this point, that has a magnetic field circulating around it, and an X component receiver is the one that's best coupled, and that explains why this X component had much bigger negatives than the Z component in the GATEM survey. Okay, so we ran a batch of models. They confirmed that a polarizable thin sheet, so we had our system up in the air with a separation S, either 0 for coincident loop or 300 meters for a sling-ram type geometry. At systems at some altitude, we've put a conductive layer at depth and potentially polarizable. So on the left is the B field. If you had a B field sensor, the bottom dBdt, polarizable or is dashed, non-polarizable straight, and a polarizable one is quite detectable at depths at surface 100, 200, 400, and 800 meters. So a B-field system with the noise levels we had in a million amp meter squared dipole moment transmitter could see a polarizable layer 800 meters down. There's no X component at the center of the loop, so you see nothing. If you go to sling-ram geometry, if you look at the B fields, the X component is in red. The Z component in black. Solid is non-polarizable, dashed is polarizable, and with a sling ram geometry, you could easily see deep targets in the X component better than the Z. So all of that sort of made sense. So based on that, there was a couple of the Myra projects run from 2010, 2011, sponsors Antler Spectrum, Tech, BHV Billiton, Outer Rim, and Abitibi. So there was one contractor, two potential mineral explorers contractors, and two miners. And the number of sponsors was limited because it was not an expensive project and trying to keep things exclusive. Stage 2 commenced February and ended in 2013. Stage 3 was not funded for varying reasons, which I'll get to in a minute. So the aim was to develop airborne IP hardware. So 3 companies had done modeling studies, which said that if you use B or DBDT receivers, you could, at low frequencies, you should be able to see IP over porphyries. RMIT, where I was employed, had an electric field sensor, non-contacting one, and I calculated that the E fields, if we could measure them, would be much better than B or DBDT. So the lab sensitivity of our non-conducting sensor was 10 nanovolts per meter. Okay, so we did some tests before flying. We knew that B fields would suffer from rotation noise. So if we have a sensor with 0.1 picotesla sensitivity, that's actually 500 million times smaller than the Earth field. So if the sensor rotates, just its sensitivity to the Earth field gives you a changing response. So this is our sensor being towed on a trailer. The first 7 seconds, actually not these weren't seconds, oh, well, there might have been. The first 7 seconds it was moving, so you've got a lot of the rotation was being measured, X, Y, and Z components. It stopped at around 7, and then that's just the suspension system winding down to the right. At the same time, we're measuring B fields, X, Y, and Z components, and you can see they're mostly sensitive to rotation. We also measure DBDT, the conventional EM sensors. That shows up all these spikes, spherics, and those spherics also show up in the B field, the bigger ones. The other thing DBDT showed up was VLF signals in the 3 E components. VLF was from a Navy communication station about 2,000 kilometers away. So VLF was the main sort of source of signal. So this was from Northwest Cape. Okay, so we knew that rotation was going to be an issue with B field. But anyway, we wanted to test electric fields as well. So this was vehicle testing. That's a non-contacting electric field sensor. This pole is an attempt to short out the variable Earth ionosphere gradient, which is hundreds of volts per meter. We ended up, the sensor didn't collect any useful data, mostly because there's tons of charge on dust. There's radiation, there's radon in the atmosphere decaying to alpha particle, spitting out alpha particles. The electric field sensor worked in a Faraday cage, but not in the air. This is just a picture of us flying the electric field sensor. And the magnetic field sensor. So we did a test. We had a transmitter on the ground and a target loop with a capacitor to test sort of IP. We flew that. This is measured rotation data, measured B field data with lots of rotation noise. The bottom is dBdt. This is flying over the transmitter. And our other loop is out off to the side. We can process bits of the data. But this picture on the left shows detection of a capacitor in the ground. So with its sort of negative sign. And so at the end of stage 2 of the Elvira project, we had a test over synthetic target that was successful. One of the sponsors, Outer Room and Source, they offered to fund the test of the system over a sulfide deposit because we spent the project budget at that point, and the other sponsors and RMIT agreed to delay an expensive stage 3 till this test happened. So at that point, Outer Rim also attempted to reduce the size of the bird and collect data with a batch of flights over the next year. At that point, Outer Rim entered receivership and work ceased. So the stage 3 precursor of a test over a known target was never achieved. And Elvira gave up on it and the sponsors gave up. Between 2015 and 2019, BibTem was developed. Thomson Aviation, Monex recommenced system development. They did new suspension systems in birds, had tests with a ground loop source, built multi-channel systems with acquisition hardware, high power transmitter, 1 million amp meter squared. Worked on rotation fitting software. We proved that Russian rotation sensors were nonlinear and useless, and the project went on the back burner. So just returning to what you wanted for an IP system, we want low frequencies from an IP system, but we also were interested in massive sulfides, which have got sort of higher frequency responses, and mapping, which is geologically useful. There were various things looking at which sensors could do things. There was the one that we tested with the Elvira project. There were SAM systems, which measure the total field component, which would have the horizontal component in India and the vertical one at the poles. Squids were too difficult, flux gates were too noisy. Farley had a system that weighed 2 tons, and which, when they tried to get it off the ground, the loop broke. But anyway, with Newmont sponsorship, we resurrected the BibTem system, replaced the sensor. We flew a slinggram survey. That's the transmitter. Back there is the receiver. We had issues like the tail on the bird had insufficient drag. But what killed this particular problem is that the host rock was 10,000 ohm meters, and it was too resistive to have enough current for detectable B fields. So that was a test that showed there are limitations with the magnetic field sensors, which electric field would have solved, but we couldn't get to work. We did another flight with the dual helicopter systems. This one, I can't show you any results, but relatively small IP targets were missed. At which point we did some more modeling, looking at finite rather than layered Earth targets. And If you look at the right, that's the response with no IP effect. And that's the one with IP effect. So we've got clear negatives in the Z component, clear reversal. So that's with IP, without. So the concentric loop had clear responses from this target, whereas the separated loop we'd been using with a separation of 300 meters didn't. So the next thing we decided to do was to test with the central loop system. And we tested that over a couple of sheds near Griffith. The blue here is the predicted response of the shed, the biggest you could get. We saw that in the data. So a coincident loop system worked. Okay, so as of today, the status is that airborne E field has failed. It'll never work. Airborne B field is yet to work well enough for good IP. It needs rotation sensors, which we don't have, but might be in the pipeline. Airborne DBDT, based on modeling experience, is too sensitive to shallow clay conductors to see deep or see-through conductive cover. So I'm going to look into the future now as to what can we do. Well, as I said, we could improve the B field system, but first we need better rotation sensors, which we don't have yet, I'll say. So the problems that we have to solve, we need good low frequency data, which is the rotation noise, the sensors rotating in the Earth's field. That's what limits, we need to penetrate conductive cover. We'd like to detect high-grade massive sulfide ores better than the DBDT systems, which a B field system should. And we want to detect IP effects from economic rather than fine-grained sulfides, with the ones with the longer time constants. And DBDT, as I say, has 1 frequency amplitude fall off, so it's not good at low frequencies. So we want to get either B or E working. Receivers need long sensor tethers, which complicates operation and increases the amount of swinging they do and so on. And safe flight speed and economics means we have limited averaging time. So how can we, critical at low frequencies, how can we solve these? So I'm saying the solution to motion rotation noise is put the sensors on the ground. On the left, the noise of sensors in a shielded chamber is very small. If we measure on the ground, it's about 2 orders of magnitude better. That's because we've got spherics, cultural noise, etc. Suspended airborne systems, response is read from 3 different airborne sensors. At the low frequencies for IP between 10 hertz and 1 hertz down here, we're down 2 to 3 orders of magnitude if we had a sensor on the ground. If we have an array of sensors, we can use correlation. We've proven we can reduce noise by 1 to 2 orders of magnitude. So we can get another 1 to 2 orders of magnitude reduction from conventional ground sensors and get 4 to 5 orders of magnitude improvement in IP type measurements. Okay, so the locust array vision. This is an ExxonMobil patent, which has various holes in it. But we're looking at ground-based EM receivers flowing an airborne transmitter. They were looking for hydrocarbons. They said this would be a good way to go. Before that, Bengate and others introduced sort of ground floor. This data on the right, every time I move the mouse, the screen jumps. has one single transmitter here at G. So that's one transmitter. And they flew a survey at the black line shown, and they plotted the response where the transmitter was, not where the receiver was. And this clearly showed a small massive sulfide target 200 meters away. So this type of map is you plotting at the transmitter with a single receiver. This was a relative high, this is a relative low when the plane was over here, but when the plane was flying this line over the target, there was a plus. Whoops. Okay, I'll skip that. So modeling shows we can use fairly widely spaced lines with increased resolution. What is shown here is this particular here is a bit like that ground floor I just showed you. Here's the target. And this, with a sensor here, with each of these things plotted the transmitter, we get a fairly clear response. Each of the other ones is with a, for example, this panel here shows the response when our receiver was sitting there, and we plot that at the transmitter. So numerically shows that something like 250-meter spaced stations and flight lines are fine. And you can do the same thing for a larger target, say 200 by 400 meters. You can get away with 500-meter space ground stations, 500-meter airborne line spacing. Detection was obvious from modeling. So this was sort of an EM target. And this system would be ideal for IP as well as EM. So your typical porphyry target, for example, is something like 1 kilometer across with 500-meter alteration surrounding. Porphyries might be a sort of an ideal target. So I called these locust stems because this array of sensors is a bit like a plague of locusts that collect everything. I'm suggesting they should be developed to operate with existing airborne transmitters. The advantage of a ground sensor is we can plug in electrodes or use non-contacting electrodes as well. So that completely solves the airborne EM issues of motion noise, aircraft noise. You can have a B field sensor because it's not swinging around. And so you get better conductive cover penetration and deeper exploration. Measuring E fields, we get detection of resistive as well as conductive targets. You can get longer stacking times than you do in flight because you're not trying to work with quite such high resolution. There's no null couple targets, so it doesn't strike angle, doesn't matter, you can fly in any direction. What it needs is inexpensive mass-produced B&E sensors and a significant investment to realize this. For IP, the fact that we're measuring E as well as B makes IP a second-order effect rather than a third-order effect. Huge increases low frequency signal to noise. A 3 hertz transmitter, which is quite easy to fly, not easy to measure the response airborne, but we will fly a low frequency transmitter, should be sensitive to sulfide IP effects to much larger grain sizes. So there are challenges. If you look at today, you probably need 30K for a ground node with an induction mag. But realistically, we priced systems that could shrink that cost to about $1,000. That's Australian per node. You're going to need significant software development acquisition. If you want to use unmanned aircraft, beyond line of sight might be potentially used for planting and retrieving receivers. There's issues you want to be absolutely certain that avoid the transmitter flying thing, and you've got range and payload issues for efficiency. But if you're looking at exploration in the Andes for copper, 3D surveys could use contour flying and convenient access stations placed by unmanned aircraft. So you'd actually get good IP surveys using a voltage source rather than the dangerous and difficult current sources that require tracking in huge amounts of water. We measure EE plus additional B components, and we've got the E field sensors good for highly resistive areas. There's no need for a consistent flight direction. You can just do contour flying, so it's much more efficient for aircraft and helicopter safety, lower and more consistent ground clearance rather than trying to fly up and down hills. If we use tripod and non-contacting E-sensors and an unmanned aircraft, we should be able to find somewhere to place them within 100 or 200 meters of desired grid locations, which might be 500 meters apart. So this system could revolutionize exploration in something like the Andes or on flat-lying ground where placement is easy. So that's the end of it. And the first question that someone might ask is anyone planning to put locus-tem into practice? And a company called TerraDelv is proposing an environment project to do just that. So I'll stop at this point and take any questions.